Right. So let's quickly go through what we had discussed in the last class and we'll resume from there. So we discussed the basic definition of current, solved a few problems based on that. I is equal to dq by dt, average current delta q by delta t. I even told you how to find out the average value of any function in a given interval. Integrate the function and divide by the interval, right? Then we discussed how to set up current in a conductor. What are the factors on which it depends? Okay. How the current or resistivity depends on material, temperature, all those things. Fine. Okay, let us continue from there. If you have any questions from what we discussed in the last class, you can ask. Okay. Right. Now, we derived that R is equal to rho L by A, and rho was equal to, do you remember the exact expression for resistivity? I think it is Ne square tau divided by M or something like that. Anyway, I think it is Ne square tau divided by M. And as we know, it depends on material and temperature of the conductor. So tell me.
Sir, it's M by Ne square tau.
Okay, M by Ne square tau. Fine, not an issue. Okay, now we know tau is a relaxation time. That is the average time that an electron has between two collisions. Okay. If temperature of the conductor increases, what happens to relaxation time?
It decreases, sir.
How does it decrease?
The electrons gain more energy, so they move faster.
Correct. So simply a higher temperature means more speed of random motion of the electrons, and due to that they'll have less time between the collisions. Okay. See, there is another factor also. Forget about current, electrons and all. Generally, if you raise the temperature of a material, particularly solids, what happens? What happens when we raise the temperature of a material? Or if we heat something, what happens? 11th class heat and thermodynamics. Okay, there's something called thermal expansion that happens, right? Now see, yesterday we considered a picture like this, like electrons moving in the free space between the atoms. Let's consider this. Now, as Anugraha said, if we raise the temperature, the energy of electrons will increase. That means they'll move faster. And if they move faster, they'll cover the distance between two atoms quickly. That's okay. But if you raise the temperature, the material also expands. If material expands, the distance between the atoms will also increase, no? So basically what is happening, because of the temperature rise, the free space in the material increases and the speed of the electron increases. Then can you tell what happens to the relaxation time? Okay, I hope you both understood what I'm saying. If the space remains the same, if the gap remains the same, but the electron travels faster, then the time taken will be less. Relaxation time will be less. But due to temperature rise, we know thermal expansion will happen. The gap between atoms also will increase. The free space will increase. So electron will have to cover more distance between two collisions with more speed. Then what do you think happens to the relaxation time?
So does it remain constant?
There is a possibility, okay? because distance is increasing, distance between collisions is increasing, the speed is also increasing, it could remain constant. But actually it depends on which is more pronounced. I mean, whether thermal expansion happens more or the increase in the speed of speed of the electron is greater in magnitude. It depends on that, right? So actually what happens is when you raise the temperature, the increase in speed is more pronounced than the increase in the space. Fine. So you should not forget that thermal expansion happens. It does happen, but the speed of the electron increases many, many more times than the amount by which the distance between two atoms increases. So it is so high that you can ignore thermal expansion altogether. What is so high? The increase in speed of the electrons is so high based on the temperature change that you can ignore the increase in free space due to thermal expansion. Okay. So as a result, what happens? Speed increase is more significant. So time constant, not time constant, sorry, relaxation time decreases. And if relaxation time decreases, what happens to resistivity of the material? In the formula for resistivity, relaxation time is in the denominator. If it decreases, resistivity has to increase. In fact, there is this other factor also on which resistivity depends. Can one of you quickly tell me what N stands for? What does N represent?
Number of electrons per unit volume.
Number of electrons per unit, number of conduction electrons per unit volume. Now in a given conductor, the number of conduction electrons is fixed because each atom may contribute 1 electron, each atom may contribute 2 electrons, number of atoms is fixed, no? Now when you raise the temperature, thermal expansion will happen. Now N here, small n, is the total number of electrons divided by volume of that material. Volume of the conductor, I should not say material. Okay. Now if you raise temperature, volume will increase. If volume increases, N as a whole decreases. Okay. So number density decreases, relaxation time decreases. Due to both factors, resistivity will increase effectively. Okay. So generally, when temperature increases, time constant and number density decrease. So resistivity increases. And if resistivity increases, resistance as a whole will also increase. Okay. Again, there is the change in length and change in area also that you might need to consider, but those changes are insignificant compared to the change in resistivity. Okay. So simply based on resistivity, you can tell what happens to resistance. You can ignore the changes in length and area. That is what I mean. Okay. So based on this, there is an equation of how resistivity depends on temperature and how resistance depends on temperature. That's called temperature dependence of resistivity. If you remember in linear expansion, again 11th class physics, heat and thermodynamics, for linear expansion you have an equation like this. The linear expansion delta L is equal to original length into alpha into delta T. Okay, where L naught is the original length of the object, alpha is called its coefficient of linear expansion. Okay, and delta T is the temperature change through which it is taken, or you can also write L minus L naught is equal to L naught alpha delta T. If you send the L naught that side, you get final length is equal to initial length into 1 plus alpha delta T. Okay, this is from thermal expansion. We have a very similar equation for resistivity in terms of temperature as well. Okay, in fact, it's the same equation. In place of length, you will write resistivity. So temperature dependence of resistivity, you'll get rho is equal to rho naught. What is rho? That is resistivity at a temperature T. Rho naught is resistivity at some earlier temperature. Okay, into 1 plus alpha delta T. You can write this as rho naught into 1 plus alpha. Change in temperature is final temperature minus initial temperature. Take it like this, and you will call alpha as coefficient of resistivity. Okay, just like linear expansion. And how will you be asked questions based on this? Direct. At one temperature, they'll give you the resistivity. At another temperature, they'll ask the resistivity. Okay. So directly based on this equation, you can solve. And you have a similar equation for resistance as well. Resistance at a temperature T is resistance at a temperature T naught into 1 plus, we'll call this alpha R into delta T, that is T minus T naught. Alpha is called coefficient of resistance, thermal coefficient of resistance. Okay. So if you know the resistance at one temperature T naught, you can calculate the resistance at some other temperature T using this equation. You need to know the alpha value. Okay. Now yesterday we derived Ohm's law. Can one of you tell me the formula? Formula for Ohm's law.
V is equal to IR.
Okay. Why are Seshank and Yashmit so silent? Anyway, it's actually delta V is equal to IR. For convenience, we write it as V is equal to IR. Okay. And how we derived it yesterday was something like this. We got I is equal to voltage multiplied with something, and that something we took as 1 by R. Okay. So conveniently, it is written as V is equal to IR. Remember, V is the potential difference across the conductor whose resistance is R. Okay. So if a conductor offers some resistance R, this is the standard symbol for a resistance you all would be knowing, and you apply a voltage V across its ends, then you will find that a current I that is equal to V by R passes through that resistance. Okay. So remember, to use delta V equal to IR or simply V is equal to IR, V must be the potential difference across the resistance R, not somewhere else. Fine. Okay. And we also discussed yesterday that if the temperature is constant, resistance is proportional to L by A, directly proportional to length, inversely proportional to area. Okay. Fine. Let's solve one question based on this. Suppose there's a wire, a conducting wire. Assume its initial resistance is R. Fine. Now the wire is stretched to say twice its length. Calculate the new resistance. Think about it. Now see, generally when they say wire, you can assume it's a uniform wire, means the area of cross section is same everywhere. If it's non-uniform, they'll have to specify. Okay, so if nothing is mentioned, you can take it as a uniform wire. Same length everywhere, same material everywhere. Okay, so if you stretch this wire to twice its length, what will the new resistance be? Seshank, how will you try to solve this?
You use R equals rho L value.
Okay, so R1 is equal to rho L1 by A1, and R2, the new resistance, is the same resistivity L2 by A2. Okay. What is the relation between okay, L1, L2 relation is clear. Length is doubled. What about area? If you stretch a wire, does its area of cross section remain the same or change?
Does it reduce?
What did you say?
Does it reduce?
Reduce. Okay. Any explanation for that? Why should it reduce? Okay, Anugraha, you gave the answer as 4R. So on what basis did you say it will become 4 times?
Sir, when the wire is stretched, volume remains constant. So if length is increased, area decreases.
Okay, fine. So that is an assumption we make. Volume of the wire remains constant, and we know volume is length multiplied with area of cross section. That has to remain constant. If length is multiplied by 2, means if it is stretched to twice its length, then area should get divided by 2, such that the length multiplied with area, the volume remains constant. Okay. So if they don't specify anything, you have to assume volume remains constant. So length becomes doubled, area gets halved. So A2 is 1 by 2, you can say. So from this, you will get R1 by R2 is equal to 1 by 4. So the new resistance is 4 times the original resistance. Okay. In general, instead of twice, let's say it is made n times. If length is multiplied by n, area gets divided by n. Okay. Then the resistance becomes n square times. New resistance is n square times the initial resistance. Okay. So remember, when they don't give any extra information and they tell you that the wire is being stretched by a certain amount, you'll have to assume volume is constant. Based on that, you can tell what happens to area. Based on what happens to length, you can tell what happens to its area. Then you can tell what happens to the resistance. Now, when you stretch a wire, the material is not changing and temperature also won't change. So resistivity rho will not change. That will get cancelled. That is also involved here. Okay. Now, there is another way of asking questions also. Two wires of two wires whose lengths are in the ratio 2:1 and area of cross section in the ratio 4:1. What is the ratio of their resistances? Okay, this is a direct question. You can substitute those ratios and find out. Okay, not a big deal. You can do it. Now there's another question also. If they want to trouble you more, they can involve this. Do any of you remember Poisson ratio? This you would have studied in the chapter Mechanical Properties of Solids in 11th class. I think it is denoted by the symbol sigma. It is defined for cylindrical objects. Do any of you remember? When you talk about stress, strain, I'm sure you must have learned something about Poisson's ratio. Okay, no problem. If you remember, you can tell. No. Okay, listen. Suppose there is a cylinder. Poisson's ratio is applicable only to cylindrical objects. Okay, that to solid cylinders. Okay. Let's say there's a cylinder like this. It has its own length. It has its own diameter as well. Assume original length is L0. Original diameter is D0. Now, if you stretch this, generally, if you stretch anything, length increases, the area of cross section decreases. So in this case, the diameter decreases. So what happens when you stretch it is, it becomes somewhat like this. Imagine it being stretched from both sides. Okay. So there is some change in length and there is some change in diameter as well. If length increases, Okay, that is, if delta L is positive, diameter will decrease, delta D will be negative. And if you compress it, change in length is negative, but if you compress it, it will bulge out. Diameter will increase. Delta D will be positive. Okay. Now it's not necessary that when you stretch an object, its volume always remains constant. It depends on the nature of material, and also it depends on how much you are stretching it. Okay. So this assumption is not always valid. If they don't specify anything, you will have to assume volume remains constant. But if they specify Poisson's ratio of that material, then you should understand how to use it. Okay. And Poisson ratio relates the change in diameter to the change in length. It's like this. Okay. And see, if length increases, delta L is positive, diameter decreases. Okay. So if the numerator is negative, denominator is positive. And if the numerator is positive, denominator is negative. So one positive, one negative, the overall thing will become negative. But Poisson's ratio, by definition, is to be written positive. So we put a minus sign, such that the whole thing becomes positive. That's all. Okay. So this helps you find out the relative change in diameter if you know the relative change in length. Okay, let's try one question like this. And you can simply multiply and divide by 100. And I hope you know this. Relative change multiplied with 100 is called percentage change. So negative of percentage change in diameter divided by percentage change in length. Okay, so we'll be doing a little bit of revision of something you would have studied in 11th class. Tell me, suppose you have x is equal to a multiplied with b. Okay, this is a product. And you know that, or okay, if percentage change in a is small a percent and that in b is small b percent, how do you calculate or express percentage change in x? Anyone? Don't remember. Okay, no problem. Okay. Consider the quantity A itself. Change in any quantity is written as delta of that quantity. Okay. Now, if you want relative change, it is change divided by the original value. Okay. And if you want percentage change, it is relative change into 100. So delta A by A naught into 100. Okay. Same with B, same with X. Now what we are looking for is this. I mean, we are not looking for percentage change in A, that is known to us. In terms of that, we want percentage change in X. So what we are actually looking for is delta X by X into 100, right? Now I told you, whenever you have this delta X by changes or errors, okay, yesterday we had discussed one question, no, last class. They gave the, I think they had given the changes in resistances R1 and R2, not changes, errors in resistance R1 and R2. They asked you to find out the error in the effective resistance. Okay. So whenever you need to relate small changes in quantities, no, differentiate the relation between those quantities, as I said. Okay. Now we have x is equal to AB. If x is equal to AB, let us differentiate this equation. You'll have to assume x, a, and b are all variables. Okay, because we know change in a, we know change in b, and we want to find out change in x. Means all three are variable. Okay. What shall we differentiate with respect to? It is your choice. Okay. You can differentiate with respect to any one of these variables or some new variable also. Let's differentiate with respect to time. Then dx by dt becomes, can any one of you tell me the product rule for differentiation? How to differentiate the product of two numbers, variables, sorry.
U dash V plus U dash.
Okay, uv dash plus vu dash, fine. So it becomes a dB by dt plus b dA by dt, correct? And now you can cancel the dt. That's why I said it doesn't matter with respect to what you differentiate. Okay, so now we got dx in terms of a, b, dA and dB. What we wanted was dx by x. Into 100 we can do later. Okay, so dx by x becomes a dB by x plus b dA by x. That becomes a dB by x is nothing but ab. Okay, anyway, this is all 11th class syllabus. Cancel, cancel. So you have dB by b plus dA by a. So dA by a plus dB by b. So I'm sure you all must have learned this in 11th class. When two measurements are multiplied, okay, then their relative errors get added. This is the relative error in A or relative change in A, and this is the relative error or relative change in B. As I said, for errors, you'll have to use plus sign always. Changes can be negative or positive, but errors will always be positive. Okay. Not just for x is equal to AB, generally, if you have x is equal to a to the power of m, b to the power of n, c to the power of p, something like this, then you can write delta x by x is equal to m times delta a by a plus n times delta b by b plus p times delta c by c. This is how their relative errors or relative changes are related. Same thing with percentages also. You just have to multiply with 100 on both sides. Relative error becomes percentage error. You get m times percentage error in A plus n times percentage error in B plus p times percentage error in C. Okay, fine. So I said we will solve one question based on how resistance changes when Poisson's ratio is also given to you. Let's see. Suppose Poisson ratio of that material is 0.4. Okay, remember what is Poisson's ratio? It is negative of percentage change in diameter to percentage change in length. Okay, it's negative of that ratio. Okay. Let original resistance be R if length increases by let's say 2%, small increase. Calculate the change in resistance. What change? Percentage change in resistance. Okay. By what percentage does it increase or decrease is what you need to find out. Try this, all of you. I'll give you 2 minutes. And remember, D here denotes diameter, not area. L is the length of the wire. Anugraha, which concept are you referring to? Poisson's ratio or this percentage changes?
Percentage changes, sir.
First chapter, units and measurement.
So that they in my school they say they'll teach at the end of 12th because it includes 12 concepts as well.
It includes differentiation, but without that also they could have taught. But in every chapter you'll have questions based on percentage changes. Okay. I'll see if I have recording of my lectures of that chapter. I'll share with you. You can go through them. Isha, good evening. Actually, I just noticed that the link did not get shared to you. I posted in that broadcast group, but it didn't get shared to you. So we had started the class at 7:10 itself. We discussed a little bit about how resistance depends on temperature. And we are now discussing how resistance depends on length and area. But okay, I'll share the recording with you. Or if possible, at the end of the class in another 15 minutes, I'll explain to you, okay? Any answer, anyone? Length increases by 2%. You have to calculate the percentage change in resistance. Okay, listen, this is actually a little difficult only. If you are not comfortable with percentage changes, you can't solve it that easily. First of all, now in this question, they have mentioned the change in length and they are asking you the change in resistance. Okay, so first think of how resistance depends on length. We know the formula is R is equal to rho L by A. We had derived this yesterday. Okay, you can write this as rho L A to the power of -1. Fine. Now, rho is resistivity of the material. It depends on material and temperature. It doesn't depend on length and area. Okay? So whether you stretch the wire, compress the wire, twist the wire, do whatever, the resistivity is not going to change. Now, if you want percentage change in resistance, okay, again, little bit of 11th class concepts. When three terms are multiplied, okay, it's like resistivity, length, inverse of area are being multiplied, no? So whenever terms are multiplied, their percentage changes get added. So you can say that it is equal to percentage change in resistivity plus the percentage change in its length, and the power of area is -1. So minus the percentage change in area. Now why minus? Because we are looking for the actual change in resistance. We are not dealing with errors in measurement. Okay. So last class or the class before I told error should never be negative. You should not use a minus sign. Here we want the actual change. A quantity may decrease, may increase. No, so actual changes can be negative, can be positive. So you have to take the sign as it is. Okay. Now resistivity is constant. So percentage change in resistivity will be 0. Now in the question, it is told to you that the length increases by 2%. Okay. But you still need to know what happens to the area. Then you can tell what happens to the resistance. Okay. And to find out what happens to the area, you can make use of this. That is Poisson's ratio. Poisson's ratio doesn't involve area directly, but it involves the diameter of the wire. Using diameter, you can connect this to area. Let's see how all that can be done. Area of cross section is equal to pi r square. Okay, we assume it's a circular wire. And this can be written as pi d square by 4. Because radius is half of diameter, r square becomes d square by 4. So this is how area is related to diameter. Okay. If A is pi d square by 4, then percentage change in area will be percentage change in pi by 4 plus the power of d is 2. So 2 times the percentage change in diameter. And pi by 4 is a number, it won't have any change. So 0. Therefore, percentage change in area is 2 times the percentage change in diameter of the wire. Okay, now we see the connection between all the quantities that we need. You are given the Poisson's ratio of this wire 0.4, and 0.4 is equal to negative of percentage change in diameter by percentage change in length. So we can use that and write 0.4 is equal to negative of, we still don't know the percentage change in diameter, divided by percentage change in length is 2%. So negative of percentage change in diameter becomes 0.4 into 2, 0.8%. That means percentage change in diameter is minus 0.8%. And it makes sense. Length increased by 2% means we stretch the wire, then diameter has to decrease. Okay. And that's why we have a minus sign in percentage change of diameter. So minus 0.8%. Put that here. You can then say that the percentage change in area would be minus 1.6%. Okay. Now put that here. Minus 1.6%. Minus of minus becomes plus, and therefore the percentage change in resistance becomes 3.6%. Okay, so let me explain this question once again. Basically, it's a case where a wire is being stretched and you have to find out what happens to the resistance. Okay. And here the wire is being stretched by a small amount, 2%. And you are asked to find out the percentage change in it. It's not like length is doubled or anything like that. Okay. In fact, this Poisson's ratio also will be valid only for small changes. Small percentage changes. How small is small? Anything less than 10%, you can use this. Changes less than 10%, you can use. More than that, you should not use. Anyway, all this is 11th class stuff only. We'll not spend much time on this. So length increases by 2%. You are asked to find out the change in resistance. So we first think of how resistance depends on length and area. Okay. We know resistivity rho does not change. Length changes, and if length changes, the area of cross section could change. If you stretch something, the area decreases. If you compress something, the area of cross section increases. It bulges. So now from the change in length, or based on the change in length, we had to calculate the change in area, but we don't have a direct relation between them. This is not a case where volume is constant. If volume is constant, you could have done it like the previous question. L into A is constant. So if length is doubled, area becomes halved, and so on. You could have used something like that. But here that is not the case. You are given the Poisson ratio of this wire. Okay. And Poisson ratio sigma relates the percentage change in diameter to the percentage change in length. Percentage change in length was given in the question. Poisson ratio was given in the question. With that, we calculated the percentage change in its diameter. And using the percentage change in diameter, we calculated the percentage change in its area. And finally, we could tell the percentage change in resistance. Okay. I'll send you some more questions like this for practice. This is important. Okay. Like very frequently, you'll be asked questions where wires are stretched, two wires are combined, one wire is cut into several parts, and so on. Okay. And percentage changes are very, very important. I'm telling you, if you find time during this weekend or any time, you learn how to calculate percentage changes. Okay. If I have a recorded video of that, I'll send you. Okay. Fine. Next is applications of Ohm's law, KCL, KVL. Fine. Now see, we discussed yesterday how to set up current in a conductor, right? It's not necessary that conductors will always be uniform like this. Okay, the area of cross section may decrease at some points, it may increase at some points. Okay, it need not be same throughout. Okay, and you can connect multiple conductors also. And you apply a voltage across it, current will flow. Okay. Now, there is one assumption that we make, okay, in this chapter and also all the chapters that follow on from here. There is one assumption that we make. If we consider any cross section Okay, let's say there is a voltage applied across this conductor or conductor combination, whatever you like to call it. Apply a voltage. We know battery will circulate electrons, right? Now you consider any cross section anywhere, the amount of current flowing into that cross section should always be equal to the amount of current flowing out of that cross section. Means the number of electrons coming into that cross section should be equal to the number of electrons leaving the cross section in a given amount of time. Inflow of charge should be equal to outflow. Okay, that is what we call as steady state. Inflow of charge at any cross section should be equal to outflow. That is an assumption we make in your syllabus, and that must be obeyed everywhere. Okay, so let's say in this part of the conductor, the current is I. Then in this part of the conductor, should the current be I itself or something else? If that assumption is obeyed, if there is no charge accumulation anywhere, inflow of charge is equal to outflow of charge, will the current be the same everywhere or not? What do you think? At any cross section, okay, whether it's a junction between two wires, multiple wires, or in a single wire itself, you take a cross section anywhere, inflow of charge should be equal to outflow. So should the current in both parts be same or not?
Yes.
It should be same. Okay, you consider this junction. See, by convention, we know current is the direction of current is the direction of flow of positive charges, right? But we also know that it's actually electrons that flow in conductors. But let's assume positive charges are flowing. So if you consider this cross section, the number of positive charges entering into that cross section in a given amount of time should be equal to the number of positive charges leaving that cross section. So whatever is the current on the left side, same should be the current on the right side. Same will be the current everywhere. Okay. So if there are no junctions in between, junction means three wires should be connected, three or more wires should be connected. If there's nothing like that in between, at every cross section, you will see the same current, same rate of flow of charge. Because if the rate of flow of charge is not same everywhere, then at some points, inflow must be more than outflow or outflow must be more than inflow. We don't consider such situations in your syllabus. Okay, you only have cases where inflow is equal to outflow. Right? So we'll consider it like that. So in a single branch, whether there's only one conductor or whether there are multiple conductors, whether there are resistors, capacitors, batteries, whatever it is, in a single branch, the current must be same everywhere. Okay. Later on, you'll learn about something called an inductor also. Okay. These are the basic current elements, circuit elements that you are going to come across: battery, resistor, capacitor, inductor. Okay. So whatever be the elements present in a single branch, if there is no extra wire connected in between, means if there is no junction anywhere, all the elements will have the same current through them. Okay, everywhere in that branch, the current will be the same. So remember this property, we don't allow accumulation of charge anywhere. Okay. So at any point in a circuit, inflow should be equal to outflow, right? And based on this fact itself, that inflow should be equal to outflow, like inflow of charge is equal to outflow. Based on this, we have something called the junction rule, or Kirchoff's current law, KCL. Kirchoff, Kirchoff, it's your wish, you can pronounce it whichever way you are comfortable. So the law suggests that itself, if there's a junction of wires, let's say there is a current I1 flowing in and there's a current I2 flowing in. Then in the third wire, see at the junction, we have considered two inflows. Then in the third wire, there must be an outflow. And outflow should be equal to inflow. So I3 is equal to I1 plus I2. Okay, so that's the basic idea behind KCL. And we'll be applying this in every circuit that we come across from now onwards. Inflow of current to a junction should be equal to outflow. Okay. Suppose there's a junction like this. There's 2 ampere current going out from this in this wire. There's 3 ampere current flowing in this wire into this junction. 6 ampere current flowing into the junction. What is the magnitude and direction of current in the fourth wire? Try to answer directly.
7 amps are
7 amperes
outward.
outwards. Okay. Inflow is equal to outflow. Now, as you can see, there are two inflows, 3 and 6, that is 9. Then there's one outflow 2 ampere on one side. Then the other side, there should be an outflow of 7 amperes. That way. And see, sometimes you may not know whether you may not know the direction of current in a particular wire. In this case, it's obvious. You see the inflows and the other outflows, you can tell whether it's outflow or inflow in the last wire. Sometimes you may not know the direction of current in a particular wire. In such cases, what you do, you assume whatever direction you want, write the equation properly, you will get the correct answer. What I'm saying is, suppose you didn't know whether it's going to be an inflow or an outflow, and you assumed it to be an inflow I. Just write the equation based on that. So what are all the inflows now? I is an inflow, 3 ampere is an inflow, 6 is also inflow, is equal to the only outflow is 2 ampere. Okay, so you get I is equal to 2 minus 9, that is minus 7. What does the minus indicate? It indicates that the direction you considered is wrong. Okay, so sometimes when you don't know the exact direction of current, you assume whatever direction you want, write the equation properly, you will automatically get the correct direction. Okay. Right. Have any of you ever noticed how much current our everyday household devices use?
5 amps, I think.
How much?
5.
Which device do you think uses 5 amperes?
I vaguely remember seeing 5 amps written on a mobile charger adapter.
No. Mobile adapter, I'm sure you must have seen 5 volts, not 5 amps.
Oh, yeah.
Most of the digital devices that we use, okay, mobiles or laptops, they operate on 5 volt voltages. Okay. That's why if you touch a charger pin also, you won't get a current shock. Okay, if the adapter is working correctly, you won't get a current shock because it will be supplying a very low voltage to that battery, to the mobile battery. Any idea of current, how much current they actually draw? Okay. See, actually a 1 ampere current is a very strong current. In fact, if 1 ampere passes through our body, we will feel a shock. Okay. And sometimes we do feel a shock when we touch some electrical devices like that. So some devices are there which use more than 1 ampere current. There are many devices which use less than 1 ampere current. Let me see. I think a mobile charger, I think draws 1.5 ampere if I'm not wrong. Let me check. It's written, input voltage. Okay, this is a laptop charger. It's written input is 100 to 240 volts. We know in a household circuit, in the power socket, we get 230 volts, 220 to 230 volts. Okay. So input is that much. And current is 1.5 ampere. Okay. Output voltage is 20 volts. Okay. Laptop adapter is giving an output voltage of 20. 20 volt is safe for us. We can touch that much voltage, not an issue. And output current is 2.25 amperes. Fine. ACs and all, I think they use even larger amount of current. They draw larger amount of current. Maybe 10-15 amperes they may be drawing. In fact, the switch you use to run an AC, that switch itself will be, on that switch itself, it will be written 16 amp switch will be used. Okay, because AC draws more current. Anyway, so just remember 1 ampere is a large current. Fine. So basically this is what is KCL or junction rule. Inflow of current into a junction should be equal to outflow. Okay. Next is KVL, Kirchoff's voltage rule. Or it's also called as loop rule, voltage law. Okay, those of you who have studied this chapter, can you tell what is KVL?
The algebraic sum of the potentials at a point should be equal to zero.
The
In a loop,
algebraic sum of
potentials in a loop should be equal to zero.
okay, potential changes in a loop should be zero, correct. See, this is something like you imagine an object. Okay, let's say there's a block. Assume it is taken along a path. Let's say it starts from A and it is taken to different places and brought back to A. Okay. Now, when it is taken to different places, it is possible that it went to a greater height, maybe some position B here, and then it went to a lesser height, some position C here, and then some other height D. Okay. Taken to a different height E, whatever it is, and let's say it comes back to this starting point. So you imagine starting from a place, going to different locations and coming back to the place where you started from. Now, along the way, you could have climbed up or climbed down the road at different points. Okay. But whatever you do, there are some gains in height. There are some losses in height, or there is an increase in height. There is a decrease in height from the ground, plus H3, plus H4, minus H5, whatever it is. Okay. But when you come back to the starting point, the sum of all these, okay, the total height gain and the height loss that you have undergone during the journey, okay, or the total gain in elevation and the total loss in elevation that you have undergone during the journey should balance out. Okay. Or you can say the net gain in elevation is zero, because sometimes the gain in elevation is positive, sometimes the gain is negative. Okay. When loss is happening, the gain is negative. Okay. So the total gain in elevation becomes zero if you return to the starting point. This same idea, if you apply it to an electrical circuit in terms of potentials, it becomes KVL, Kirchoff's voltage law. Okay. So suppose there is a circuit like this, having some resistance, maybe a capacitor, maybe a battery. And as I said, later on, you will come across an element called an inductor. It's basically a spring. Okay. So circuit could have any number of these elements, let it be. Okay. There may be multiple loops also in the circuit. For example, there could be another resistance here, and so on. Okay. Just like when you start from a particular place, you go to a place X, then you may go to Y, Z, return to X, then you go to P, Q, R, and finally come back to A. Okay. So there could be multiple loops also along the journey, not an issue. But let's say you started from here. When you start from here and you move along this circuit, there are some elements that you come across, right? Now, a resistor could have a potential difference across it. We know from Ohm's law that delta V is equal to I into R. When current is flowing through a resistance, there must have been some potential difference. Okay. So when you move from one side of the resistor to the other side, the potential may increase a little bit, or it may also decrease, depends. We'll discuss that in detail. So some change in potential will happen. Let's call it as delta V1 or delta V across the first resistance R1. Continue moving along this loop. Then you come across a capacitor. We know if a capacitor is charged, there will be potential difference between its plates, right? So when you go from one side of the capacitor to the other side, you may come across a change in potential. Let's call it as delta V of the capacitor C. Next, continue moving along the loop. Then you come across this inductor. Okay, inductor, as I said, you learn later, but inductor also is an element which can have a potential difference across it. Especially those of you who are learning electromagnetic induction, Okay, you will soon come across this. It's just a coil which has EMF across it. Okay, how that EMF is produced and all you learn. So, but there will be some potential difference across it. Okay, let's call it delta V L. L is the symbol we use to indicate an inductor. Next, battery. We know battery definitely has a potential difference across its terminals. So delta V B, potential change across the battery. And you come back to the starting point. Since you return to the point where you started from, the final potential should be equal to the initial potential. Means the total change in potential along the loop is zero. Obviously, if you come back to the same point where you started from, the total elevation is zero only. Total change in height is zero. But along the way, you could have climbed uphill for some time and gone downhill for some time. So heights may have increased or decreased. But when you come back to the starting point, total change in height becomes zero. Same thing here. So we can say that potential difference, not potential difference also. Be very particular here. You have to call them potential changes. Okay. There's a difference between difference and change. Can any of you tell me? Okay, I don't know if we discussed this before or not. What is the difference between 5 and 3?
2.
2. What is the difference between 3 and 5? Between 3 and 5 also it is 2 itself. Okay. Difference is something which is never negative. By definition, it is like that. Okay. But changes can be positive, they can be negative. If a quantity increases, the change is positive. If a quantity decreases, the change is negative. So there is a difference between saying potential difference and potential change. Okay, let's consider an example. Assume there's a battery. We know battery maintains a potential difference. Let's assume this is that common household battery that we use. What is the voltage of that common household battery? Or EMF? On the battery that is inserted in a TV remote, what is the EMF? 1.5. Single battery 1.5. We use two batteries to make it 3 volt. Okay. Anyway, the button part is the positive side. The button side is the positive side. The opposite side is the negative side, negative terminal of the battery. Let's say this is a 1.5 volt battery. Let's call this point as X and this point as Y. Now this 1.5 is the potential difference. We'll always say it is 1.5 only. We'll never say minus 1.5 because difference will never be mentioned negative. Okay. But when you move from X to Y, you are going from negative terminal to the positive terminal. You are going from low potential to high potential. Then the change is always final minus initial, right? Final is Y, initial is X. We know potential at Y is higher than potential at X, then this will be plus 1.5 volts. The change will be plus 1.5. But if you go from Y to X, that is from positive terminal to the negative terminal, then the change, okay, I don't actually have to write change again, but just to show that we are talking about change, it will be final, that is potential at X, minus initial, that is potential at Y. Now it becomes minus 1.5 volts. So potential difference is 1.5 only, but potential change could be plus 1.5, minus 1.5, depending on how we are moving across that element. Okay. So same thing here also. This is the one thing that you need to be very careful with when you apply KVL. Okay. So the sum of all potential changes that you come across in a loop will definitely be zero. And why will it definitely be zero? Because you are returning to the point where you started from. That means you are returning to the same potential from where you started. So your final potential is equal to initial potential. That means all the changes must have cancelled. Okay. So total change in potential along the loop is zero. So you can say change in potential across the resistance R1 plus change in potential across the capacitor plus change in potential across the inductor plus change in potential across the battery must be zero. Okay. This way we will get some equations which will help us calculate a few things about the circuit, like how much current flows in it, or how much potential difference is there across a capacitor or a resistor, something like that. Okay, and you can apply this to any loop of the circuit. Now we considered one loop here, the bigger one. You could have considered this smaller loop also. This smaller loop involves one resistor and one capacitor. Potential change across the resistor plus the potential change across the capacitor also will be zero if you return to the point where you start from. You could even have gone along this loop, bypassing the capacitor, and returned like this. The sum of all these potential changes also will be zero. Okay, and this is a very, very powerful equation. This chapter, electromagnetic induction, I think the chapter after that is alternating current. In all the chapters, we'll be using KVL to derive very, very important relations. Okay, in fact, in this chapter itself, we'll be deriving something called the equation for charging of a capacitor and discharging of a capacitor. There also we'll be using KVL, meter bridge potentiometer, everywhere. Okay, so the idea is clear. It's a simple thing only. The algebraic sum, I'll just write the statement quickly. The algebraic sum of all the potential changes in any loop is 0. Okay, so to apply this, you need to know how to express potential changes. If you don't know how to write potential changes, then you can't write KVL equation at all. Okay, let us discuss this in detail. First, suppose you are moving across a battery. Okay, like when you move along that loop, let's say you are going from one side of a battery to the other side. How to write the potential change? Simple. Battery maintains a potential difference across its terminals, right? Let's say the potential difference, I'm telling difference is a positive thing. Okay, 0 or positive, it should never be negative. Let's say the difference is E. Let's call it as EMF of the battery. Okay, now we know one side is positive terminal, the other side is negative terminal. Let's call this as X, this as Y. When you move from X to Y, first case, like, I mean, as you move along the loop, let's say you happen to go from the positive terminal of the battery to the negative terminal. Can one of you tell me? When you move from the X side to the Y side, should potential increase or decrease?
Decrease.
Can you repeat? Your voice was not clear.
Decrease.
Decrease. You are going from the positive terminal to the negative terminal. Potential decreases. And if potential decreases, the change is negative. So you should write the potential change across the battery as negative of its EMF. Okay. Suppose while moving along the loop, you happen to go from the negative terminal of the battery to the positive terminal. Then we know that potential increases. And if potential increases, if anything increases, the change is positive. Then you will take it as plus E. So when writing potential change across a battery, you should check whether you are going from negative terminal to positive terminal or positive terminal to negative terminal. Based on that, you will be able to write the potential change. Simple. Okay, but you need to be very careful when applying this. Next, resistance or a resistor. Suppose there is a resistance R through which a current I is flowing. Let's say current is flowing to the right. Let's call this end as X and this end as Y. Now we know from Ohm's law that the potential difference, okay, this is difference, across a resistance is I into R. the current flowing through it multiplied with the resistance. Okay. Now see, we know current, the direction of current is the direction of flow of positive charges. Now, can one of you tell me, does positive charge flow or move in the direction of electric field or opposite to it? Does positive charge move in the direction of electric field or opposite to it?
In the direction of electric.
In the direction, because positive charges experience force in the direction of electric field, so they will drift in that direction. That means current also flows in the direction of electric field. Okay. Now one of you tell me, is electric field directed from a point of high potential to a point of low potential, or is it from low potential to high potential?
High to low.
Good. Electric field always points from a position of high potential to a position of low potential. Now here, current is flowing from X to Y, means X is at high potential and Y is at low potential. Okay. So the left end of this resistor is at high potential, the right end is at low potential. That is what it indicates. Now see, first case, when you move from X to Y, X to Y means when you move in the direction of current. Why are we talking about moving and all? As I said, when you move along a loop, okay, it is possible that you come across some resistors, right? So you'll be going from one side of the resistor to the other side. So in that process, if you are going across the resistor in the direction of current, then what will happen? Potential decreases. Potential decreases means the change is negative. So you should take delta V across the resistance as minus IR. In the direction of current, if you are moving, it is minus IR. If you are going from Y to X, that is opposite to the direction of current. You're going opposite to direction of current means potential increases, because current flows from high to low. You're going in the opposite direction, means you are going from low to high. Potential increases. Then you will write potential change across the resistor as plus IR. Okay. So for a battery, it will be in terms of the EMF, plus EMF or minus EMF, depending on whether you are going from negative to positive terminal or positive to negative terminal. For a resistor, it will be in terms of I and R. If you are going in the direction of current, it will be minus IR. If you are going opposite to current, it will be plus IR. Okay. Another element which you have learned about is a capacitor. So let's also see how to write the potential change across a capacitor. Just a moment. Okay. Now consider a capacitor like this, standard symbol for a capacitor. Now see, we just draw the symbol like this. It doesn't mean it's a parallel plate capacitor. Any capacitor is represented using this symbol itself. Okay. Assume this plate has a positive charge. The other plate has a negative charge. Let's call this end as X and this end as Y. One of you quickly tell me, which plate of the capacitor will be at higher potential, the positively charged plate or the negatively charged plate? Which plate of a capacitor will be at higher potential?
Positive.
The positively charged plate, because field will be from positive side to the negative side. And we know field points in a direction of decreasing potential. So plus Q is at higher potential, minus Q, negative plate is at lower potential. Fine. So when moving along a loop, you may have to move across some capacitors as well, right? So when moving across a capacitor, first case, if you are going from X to Y means positive plate to the negative plate. Obviously, if you are going from positive to negative, it means potential decreases. Okay. How do we write potential difference across a capacitor, anyone? We write it as Q by C. Correct. Charge on the capacitor divided by the capacitance. So when you are going from X to Y, you will write it as, you will consider it as negative of this, because potential decreases. Change in potential across the capacitor should be minus Q by C. Okay. And suppose you happen to move from Y to X. Y to X is from negative plate to the positive plate. In that case, the potential increases, and if potential increases, the change in potential should be taken Q by C. Okay. So if you look at it this way, it seems like we can write the correct potential change only if you know which is positive side, which is negative side. But there will be many cases where you don't even know how a capacitor is charged. They'll ask you to find out what is the charge on the capacitor. Okay. Now, without knowing that, how will you take positive or negative? There is one way. Can any of you tell me how you learnt it in your schools? How did they teach you to write potential across a capacitor? Potential change across a capacitor? Okay, never mind. See, suppose you are going from X to Y. Okay. If you are going from X to Y this way, the left side is the first plate. The positive one is the first plate. The negative one is the second plate. Okay. And you see that it is negative of charge on the first plate divided by C. Okay, because first plate has the charge Q. Suppose you are going from Y to X. If you are going from Y to X this way, the right plate is the first one, the left plate is the second one. Okay. And you will again see that, see Q, when you are going from Y to X, the potential change is Q by C. You can write it as minus of minus Q by C. And how is it helpful to write it this way? It is again negative of charge on the first plate that you come across divided by C. Now you will see that the formula is same in both cases. Okay. So when you write potential change across a capacitor, just use whatever charge you gave to the first plate. Okay. You could have given plus Q or minus Q. That is your choice. No problem. You just use that charge as it is and substitute in the formula. Potential change across the capacitor is negative of charge on first plate divided by C. Okay, we'll apply this, you'll understand. Right. So this is how you write potential changes across batteries, resistors, and capacitors. This is very, very useful. This, if you know this only, you can apply KVL properly. Let us do that in one or two cases now. Consider a simple situation like this: a resistor, a capacitor, and an ideal battery. Okay. Assume battery voltage is given to you 12 volts. You know which side is positive, which side is negative. Let's say resistance is given 2 ohms. Capacitance is given, let's say 1 microfarad, or let's take 4 microfarad. Fine. Assume the current flowing in this is 4 amperes. I want you to find out what is the charge on the capacitor. Now, as I say, see, you are just given the capacitor. You don't even know which plate is positive, which plate is negative. Okay, you may say that like positive terminal of the battery is connected here, so this will become positive, and negative is connected on the other side, so that side will become negative. That's not always necessary. If this battery is the one responsible for charging that capacitor, then yes. But suppose it was already a charged capacitor, charged somewhere else and put in this circuit, then it's not necessary that this plate should be positive, that plate should be negative. Okay. So we don't know which plate is positively charged, which plate is negatively charged, but you can assume one of them to be positive. It is your choice. Okay. So we'll take the charge on this one as Q and this one as minus Q. The question is to calculate the charge. Try this, all of you. Simple idea. You need charge on a capacitor. If you know the potential difference, you can tell charge. But to find out potential difference, now this capacitor is part of a loop. So you have to apply KVL to that loop and get potential change across the capacitor. Using that, you can tell charge on the capacitor. Okay. Try this, all of you. I want answers from all of you. Calculate charge on the capacitor. Shashank, Anugraha, your answers are correct only. Isha, any answer? Okay, listen, all of you. As I said, what we need to calculate is the charge on the capacitor. If you know potential difference, you can tell the charge. And to calculate potential difference across this capacitor, we need to apply KVL to this loop. Now, some of you may say, why don't we directly use Q is equal to CV by taking V as 12? That is not correct, because the 12-volt battery is not directly connected across the capacitor. If you see, the positive terminal is connected to the resistance. Okay, not one plate of the capacitor. The negative terminal, yes, it seems to be connected, it appears to be connected directly to the capacitor, that's fine. But the positive terminal is not connected. So you can't say that the potential difference across the capacitor is 12 volt. No. Potential difference across resistor plus capacitor is 12 volt, that is fine. Okay. But anyway, let's apply KVL to solve this. Now listen, to apply KVL, you first need to choose a starting point. Okay, you apply KVL across a loop. So you have to start from somewhere on that loop. Where you start from is your choice. So I'll take this as the starting point. And you have to move along the loop. Like you have to imagine yourself moving along the loop. Which sense you move along the loop also is your choice. You may choose to move clockwise like this, or you may choose to move anti-clockwise like this and return to the starting point. It's up to you. Okay, I'll take anti-clockwise. So what I'm going to do is I am going to move along the loop this way. So first I find myself moving across the battery, and I'm moving across the battery from the positive side to the negative side like this. Isha, can you tell me, when we move from positive terminal to negative terminal, how to take the potential change across the battery? Is it plus 12 volts or minus 12 volts?
So minus 12 volts.
Good. You're going from positive to negative, high to low, so minus 12 volts. Fine. I'll write that here. Minus 12 volts. Next, I continue moving along this loop in the same sense which I have decided. Then we come across this capacitor. We have to move across the capacitor from this side to this side. Okay. Now I told you, when moving across a capacitor, the potential change should be written as negative of charge on the first plate divided by C. Now when I go in this sense, this is the first plate for me. Okay. Charge on the first plate is minus Q according to what I have taken. Now potential change across the capacitor. Okay, it's better I write step by step. Potential change across battery here is minus 12 volts direct, because we know its voltage, we can tell. Potential change across the capacitor here becomes negative of charge on the first plate divided by C. So minus of minus Q divided by C. Next, continue moving along the loop. The next element I come across is the resistor. And because I have decided to move anti-clockwise, when I move across this resistor, I happen to be going opposite to the current. Current is flowing to the right in that resistor. 4 ampere current is flowing to the right, but I am going anti-clockwise along that loop. So I'm going opposite to the current. That is my choice. Okay. It's up to you which way you move. Anugraha, tell me how to write potential change across a resistor when you go opposite to the current.
Positive. It's positive.
Plus IR. So it becomes plus 4 into 2, that is plus 8 volts. Okay. And I continue moving along the loop. I find myself coming back to the starting point. No other elements are there. Now, according to KVL, the sum of these three should be 0. So total potential change should be 0. That means minus 12 plus 8 plus Q by C. How much is C? 4 microfarad is equal to 0. That's all. So I get Q by 4 microfarad is 4. That means Q is 16 microcoulombs. I got the value of Q as 16 microcoulombs, means this plate has a charge of 16 microcoulomb, the other plate has a charge of minus 16 microcoulombs. That is the charge on the capacitor. Okay. Even if you choose to move clockwise, you will get the same answer. All the signs will get reversed. Okay. If you choose to move clockwise, you will first come across the resistor and you will be going in the direction of current. So you'll write minus IR. Here we wrote plus IR. You will write minus IR. Okay. So one minus sign will come. Again here, when you move this way, first plate is this. So you'll get minus Q by C. In the way I solved, I got minus of minus Q by C. If you move clockwise, you'll get only minus Q by C. One minus will be missing as expected, and continue moving. Then across this battery, I'll be going like this, negative to positive, then it'll become plus 12 volts. Okay. When we moved anti-clockwise, we got minus 12. If you move clockwise, you'll get plus 12. So whichever way you move, finally, since you'll be equating it to 0, whether you take all of them negatives or all of them positives, doesn't matter. Okay. Let's try one more case. Two capacitors, resistor, and a battery. Let's say this is 2 microfarad. Assume this is 4 microfarad. This plate has a charge of plus 2 microcoulomb, and this plate has a charge of plus 6 microcoulomb. Somehow they got those charges. Resistance, let's take as 4 ohms. Okay, charges are given, resistance is given. Current also you assume. Let's say current is flowing. Say 2 ampere current is flowing this way. Calculate the voltage of the battery. Solve this quickly. See, you may get the answer negative also. It means like if you get an answer negative, it means the terminals are actually reversed. Okay, it's not necessary that this is the actual polarity of the battery. Find out. Okay, I got one answer as 10.5 volts, another answer as minus 5.5 volts. We'll see. Isha, any answer? Okay, can you unmute yourself? We'll discuss.
Yes, sir.
So we need voltage of the battery. We can't use Ohm's law directly. We can't say V is equal to IR. Can one of you tell me why we can't write V is equal to I into R and say I into R and say it is 8 volts? Why is this not correct?
There are other components in the circuit.
Yes, the battery is not directly connected across the resistor. Okay, that voltage V is across these 2 points. That means this entire branch, not only across the resistor. But in Ohm's law, V is equal to IR. The V is supposed to be only across the resistor. Okay, so we can't use this. Okay, Isha, unmute yourself. We'll discuss. Yeah. So we'll have to apply KVL. Which corner do you want to start from?
So left corner.
Okay. Let's say we start from here. Which way do you want to move along the loop? Clockwise or anti-clockwise?
Anti-clockwise.
It is your choice. Okay, anti-clockwise. So we start going like this. The first element we come across is this battery itself. And if this is the polarity, we find ourselves going from positive terminal to negative terminal. So how do we write the change?
Minus V.
Minus V, correct. So the first potential change is minus V. Next, continue moving. We come across this 4 microfarad capacitor and we go from this side to this side. The first plate is the positively charged plate. How do you write the potential change across that capacitor?
Q by C.
No, the formula is minus Q by C.
Yes, sir. Minus 6 by 4.
Negative of charge on the first plate that you come across divided by the capacitance. So minus of charge is 6 microcoulombs divided by capacitance is 4 microfarad. 6 by 4 is 1.5. So minus 1.5 volts. I'm not writing the unit. Okay. Continue moving. You move across the resistor. Okay. Isha, how to write potential change across the resistor? General formula you tell me.
V is equals to IR.
No. You don't always use V is equal to IR. Okay, that is what we discussed a little while ago. Across a resistor, sometimes you'll have to use, sometimes you'll write minus IR also, sometimes plus IR. It depends on whether you are going in the direction of current or opposite to direction of current. You have to check that.
In the direction of current, so minus IR.
Here the current is flowing to the left, and when you move anti-clockwise, you'll be moving across the resistor to the left. So minus IR, correct. So it becomes minus I is 2, R is 4, so minus 8 volts. Okay. And then there's another capacitor also. As we continue moving along this loop, we come across this capacitor now before reaching the starting point. Okay, tell me how to write potential change across that capacitor.
2 by 2, so 1.
Okay. How did you say 2 by 2?
Because it's this side,
Okay,
so it won't get negative charge.
fine, fine. So here, the first plate that we come across is this one. This is the first plate. And it has a
Yes.
charge of minus 2 microcoulomb. If that side is plus 2, this side is minus 2. Then you will write negative of charge on first plate divided by the capacitance. So 2 by 2 becomes 1 volt. Fine. We have returned to the starting point. So the sum of all these has to be 0. Therefore, minus V minus 1.5 minus 8 plus 1 is 0. Okay, minus 1.5 minus 8 becomes minus 9.5. Minus 9.5 plus 1 is minus 8.5. So minus V minus 8.5 is 0. That means minus V is equal to 8.5. So V is actually minus 8.5 volts. What does V being negative imply? It implies that the battery is actually connected the other way. Okay. This side is negative terminal. The other side is positive terminal. That is what it means. Anyway, the other two answers I got don't match with this. So let me know if you have any questions or if I made any mistake anywhere.
I took delta V4 as minus 1.
Delta V4, you took it as minus 1. No, as I said, this is where you need to be very careful. You have to check the charge on the first plate that you come across. Capacitor always has 2 plates. And when you are moving across the capacitor, you'll be going from one plate to the other one. What charge does the first plate that you come across have? That you have to take, and negative of charge on first plate divided by C. You can't blindly write minus Q by C always. Okay, that won't work. And Anugraha, what mistake did you make?
I'm not sure, sir. I'm seeing.
Okay, fine. So yeah, I'll send you a worksheet tomorrow. Practice as. Tell me.
So since the current initially is is in the anti-clockwise direction. For that capacitor, do we consider the right plate as positive right?
No, can you repeat? Current is to the left as shown.
Yes, sir. Do we consider the right plate as positive?
Not
If
necessarily.
if I take KVL loop as clockwise, do I consider it in the opposite direction?
Okay, suppose we moved clockwise. Then you will be writing, okay, from that cross, if you move clockwise, the first thing you come across is the 2 microfarad capacitor. So you will be writing minus, why is this like this? Okay, just a moment. Negative of charge on the first plate, 2 micro. Because when you move clockwise, this plus 2 microcoulomb is the charge on the first plate that we come across. So negative of 2 micro by 2 micro, that way you'll write. Then across the resistor, you'll be going opposite to current. So plus IR plus 8. All of them will have opposite signs if you move that way. That's all. Is it clear?
For the last capacitor, it would be negative. Minus is like
Negative of negative. Because for the other
why
capacitor,
negative of negative?
because see the
I
right
took
side
that as
plate.
negative.
Okay, we'll see. What is the formula for potential change across a capacitor that I told you?
Q by C.
No, I didn't tell you Q by C. I told negative of charge on the first plate divided by C. Okay,
Yes,
this
sir.
is how you express potential change across a capacitor. Now, when you are moving clockwise, the first plate you come across is this one. And that will have a charge of -6, right? Then you will write the potential change as negative of charge on the first plate divided by capacitance. And the minus minus will cancel. It will become plus.
Yes, sir.
So always remember it as negative of charge on first plate divided by C. It will always work. Okay. So yeah, I'll give you like 10 to 15 questions in the next worksheet simply based on KVL. Solve all of them, okay? And I'll give you answers also so that you can check whether what you have done is correct. Without answers, this exercise won't be very useful. Okay. So if you have any questions, you can ask. Let's quickly go through what we discussed in today's class. First, we talked about temperature dependence of resistivity. Okay. Then Ohm's law, just the formula Ohm's law and what delta V means. When applying Ohm's law, as I said, delta V is the potential difference across the resistance R, not somewhere else. Then we discussed how resistance depends on length and solved some problems based on it. We included Poisson ratio in those problems. And after that, KCL, KVL, and applications. Okay, like how to write the KVL equation that we have seen. Okay. So if you have any questions, you can ask. Otherwise, Isha, you stay, others can leave. For Isha, I'll just quickly revise the first 15-20 minutes of the class.
Thank you, sir.
Okay. Yeah, so in the last class, we had derived this formula for resistivity of a material, right? M by Ne square tau. M here is the mass of an electron. N is the number density. E is the charge and tau is the relaxation time. So what we talked about first today is what happens when we raise the temperature of the conductor. Isha, tell me generally, when we raise temperature of a material, what happens to it?
So it expands.
It expands, correct. Thermal expansion will happen. Good. Means volume will increase.
Yes, sir.
Volume increases and space between atoms, the free space between atoms also will increase. Correct. Now, if volume increases, this value small n is the number density of electrons, means number of electrons per unit volume. Okay. Now, total number of electrons in the conductor is not going to change. But if temperature increases, the volume will increase. So the number density will come down. Okay.
Yes, sir.
So number density decreases. And tau here means relaxation time. What is the meaning of relaxation time?